I wish my students started to clap for me at the beginning of each one of my lectures. What a warm welcome. I would like to thank the organizing committee for the opportunity to be here today. I will tell you that this is a dream come true for an academic like myself. It takes a lot of effort to find people willing to fund our research. It takes a lot of effort to find students and to train students to go out into the field and to collect the data that I'm going to be showing you today. It takes a lot of effort to collect that data and then to interpret the data and to submit the data to get it published. Then you fight with editors for a little while. And then after you go through this arduous process, you're lucky if your paper gets published and then it gets buried in a journal someplace and that's the last anybody sees of it. And so I'm delighted today to have you as a willing audience that have invited me here today to talk about these things, to actually dust off those journals and to bring this data to life. This is a delightful opportunity for me. As was explained, my name is Jaron Hansen. I'm an assistant professor in the Department of Chemistry and Biochemistry here at BYU, and I've been here for about 5 years now. Let me start with this first slide. This is what I'm going to call my roadmap of where we're going to go for the next couple of minutes. And I've already primed Dr. Pope that we got a few minutes of a late start, so I'm going to take 5 minutes from his talk. All right. I recognize that there's a number of you here that are professionals and understand a lot about air pollution, but I'm an educator at heart, and so let's spend a couple of minutes talking about air pollution. Let me tell you what it is, some of the criteria pollutants that we're interested in. Then let's move to a historical perspective. Thanks to a lot of people, in part, some of them are in this room, like Dr. Pope, we're going to look at pollution through the years here, and we're going to paint a global picture first, actually a national picture. We're going to look at air pollution here in the United States, and then we're going to bring it a little bit here closer to home. We're going to look at how air pollution has changed here across the Wasatch Front, and Utah and Salt Lake Valleys. I'm just going to touch on briefly on the effects of pollution, and I will be, here's my confession for this morning. I am not an MD, I'm a PhD, and so we're going to let the MDs that have been invited to speak talk more about the effects of pollution, and Dr. Pope, who has made a lifetime of study about this, more qualified to talk about that, so we'll just touch on this briefly. And then we're going to get into some work that our group has done. This is the sources of pollution here in the Utah and Salt Lake Valley, something that we specialize in, is measuring the composition of the pollution that we have here, specifically the particulate matter, the aerosols. And then, not to point fingers, but we kind of will point some gentle fingers in the direction of people that are responsible for that. And frankly, a lot of us are in this room. And then I will propose some solutions. First of all, air pollution. There are 6 common air pollutants. We call them criteria pollutants that the federal government sets standards for. Those are the following: particulate pollution, sometimes we call it particulate matter. Aerosols is another name for it. Ground level ozone. You guys are familiar with the ozone hole. We like to have ozone up high in the stratosphere, between 25 and 30 kilometers up. That's good ozone. We don't like to have ozone down here where you and I are standing, down here in the troposphere. Carbon monoxide. Sulfur oxides, and more in particular, we like to talk about sulfur dioxide, SO2. Nitrogen oxides, NO and NO2, and finally lead. Now, in the interest of time, we're going to focus on some of the most widespread pollution. That's particulate pollution, and I've highlighted that and underlined it, and also ground level ozone. And again, in the interest of time, we have an ozone problem here in the state of Utah as well. And there's some places specifically here in the state of Utah that have caught my interest that are not widely publicized, but out in the Uinta Basin where there's nobody. Who's from the Uinta Basin? Can you show my hand? There's nobody out there in the Uinta Basin. But they actually have a big problem out there with ozone. In fact, they're very quickly going to become a non-attainment area, and we'll talk about that in a second. But for the interest of, again, in this talk, we're going to talk about particulate pollution. So, what is particulate matter? What is particulate pollution? If I were to go outside today, and I've got this beautiful backdrop, and if I were to collect a meter cubed worth of air, so imagine I gave you a yardstick, a yard and a meter are about equal to one another, and if I were to take a yard worth of that air, yardstick wide, deep, high, and I were to sample all the particulate matter that's in that air, in that cubic meter worth of air, you would find that the particles had this trimodal distribution, okay? That some of these particles, and I'm going to go up here and point here, a lot of these particles would be 10 microns in diameter and smaller. We call these big particles right here, and coarse particles is what we call them. Usually these particles are mechanically generated, so as you guys are driving down the roads, your tires are wearing away, you're making some of this particulate matter. When you step on your brakes, you'll generate some of this coarse particles. When the wind blows as well, and the wind kicks up some of this crustal material, these are big particles. Now, these particles that are 10 microns in diameter are important to us, but frankly, our bodies really do a pretty good job of filtering out PM10. Particulate matter 10 microns in diameter and smaller. In addition to that, these kind of particles have relatively short lifetimes in the atmosphere. Because they're so heavy, they have a tendency of falling out relatively quickly. And you'll be familiar with this. You've run this experiment yourself. When you guys are traveling down a dirt road and you'll see that plume of dust that you kick up behind you. A lot of that is PM10. And you'll know if the wind isn't blowing, it doesn't take too long before that dust cloud just settles out. If we were to continue to sample the particles and look at their size distribution, I've circled some other, this bimodal distribution here. This is the fine particles. And we like to talk about these particles as being in diameter 2.5 microns in diameter and smaller, okay? Fine particulate matter. These are the particles that we're really concerned about for the most part because they have a tendency of getting lodged down deep into our lungs. It exacerbates pre-existing problems if you have asthma and other kind of things. But we're going to let Dr. Pope and some of these other guys talk about that. Okay? Trimodal distribution, coarse particles, PM10 and smaller, fine particles, PM2.5 and smaller. I'm a visual learner. And so years ago when I started studying particulate matter, I wanted to kind of put this into perspective. And I like to see the things that I'm studying. That's hard for a chemist to do. And so the slide that I'm showing you right now is actually a picture of particulate matter. On the left-hand side is a scanning electron microscope image of coal smoke. And literally what I did is I asked one of my students one day, go down, and we've got some facilities there in my lab, and I said, I've got a coal burning fireplace down there, and I want you to throw in some coal, and I want you to collect some of this coal on a filter. And so you'll see the little black dots. These are the filter pore, or the holes in the filter. These little white specks on here are actually the particulate matter that's produced, the smoke that I'm collecting for the combustion of coal. On the right-hand side, this is wood smoke. And you can see that there's a difference here. See this kind of wispy, it's kind of granular and clumped together. This is smoke that I've collected from burning of wood smoke. Now to put this all into perspective, I've superimposed on here a picture of a human hair. And human hair takes on, it depends on if you have fine hair or coarse hair, but this piece of strand of hair I've magnified 200 times, and we'll say that the diameter of that hair is about 100 microns. And so if we're talking about PM10, particulate matter 10 microns in diameter, you could pile 10 end-to-end pieces of particulate matter across this strand of hair. And if you're talking about PM2.5, you could put 40 of those things end-to-end. That's how small we're talking, okay? This is small stuff. Historic trends in air quality. I think that this plot, and it's one that I've lifted from our nation's air status and trends 2008, published by the US EPA. This is an amazing figure to me, okay? It's not all bad news. What they've plotted here as a function of time, that's on the x-axis here, is time. And so we've got 2 decades or so, more than 2 decades worth of time here. And then we've superimposed on there the gross domestic product since the year 1990. And you can see that the GDP in the United States has gone up by 64%. Vehicle miles traveled, that's the orange line there, has gone up by 36% over that same time frame. You would imagine with all the things that I'm talking about right now that you would expect that air pollution is going to become worse with all of these elements that are fighting against us here. We continue. Population has increased in the United States by 22% over that same time. CO2 emissions have gone up by 20%. Energy consumption has gone up by 19%. But here is something that's very telling. The green line here represents the aggregate emissions from our 6 criteria pollutants that I talked about. And they've actually decreased over that same time by 41%. I think that's amazing. And that is due in part to people like Sam Rushford and Arden Pope, who have championed some of the standards that the federal government has in place right now. Actually, the air pollution has gotten better in this nation over the last couple of decades. Let's focus a little bit closer here to home here in Utah. Now, some of these numbers that I'm going to give you are estimates because we were not measuring particulate matter back in the 40s and the 50s. But if you were measuring it back in the 40s and the 50s in Utah, and specifically here in Utah Valley, you would find that the major sources of particulate matter in our valley was from the home combustion of coal. This is what we were using to keep ourselves warm back then. And I showed you a picture of what that coal was. So people were breathing a lot of that back in the 40s and the 50s. Now, our estimate at the time was that we were measuring somewhere between 100 and 200 micrograms per cubic meter worth of particulate matter at that time. Okay, that's a small number. Okay, 100 and 200 micrograms is a really small number, but I'm going to tell you 100 to 200 is actually a pretty big number. And what I mean by that is the following. If I were to give you, again, a cubic meter worth of air, and you were to measure and weigh out the amount of particulate matter, PM10 that was in that air, it would weigh between 100 and 200 micrograms, okay? Now, that's relatively high, that's a really pretty big number for particulate matter, as you'll see. But means typically around 30 micrograms, okay? We moved to the 60s and the 70s. Now, we've begun to replace combustion of coal to keep our homes with natural gas, but we have something that's fighting us at this point. We've got Geneva Steel. And I recognize that they gave a lot of jobs to people in this valley, and they've done some good here, but Geneva Steel was also responsible for a lot of the particulate matter that we had in this valley. And so when Geneva Steel was at their heyday here, we had highs of 300 to 400 micrograms per cubic meter. And I hope to tell you, 300 to 400 micrograms is a lot. And I'll show you a picture here in a minute of what 300 micrograms worth of PM10 looks like, and it's not pretty. But means, again, about 30 micrograms. Those highs typically are occurring when we get these nice inversion events in January and February. All right, back in 1970, the federal government was smart enough to pass the Clean Air Act. And with the Clean Air Act came the National Ambient Air Quality Standards. National Ambient Air Quality Standards. You're going to hear about this again because this is really important, the National Ambient Air Quality Standards. And that caused Geneva Steel to have to begin to clean up their act with the help of some lobbyists and other people here, which takes us to currently where we're at now. Geneva Steel is out of business, and we're not burning, for the most part, coal to keep ourselves warm. And so most of our major sources here in Utah along the Wasatch Front are automobile, mobile sources. And generally, we're about 10 micrograms per cubic meter. So we've made progress over the last couple of decades. I primed you a minute ago by talking about these national ambient air quality standards. This is what I'm talking about. The federal government says, the EPA says, that here are these 6 criteria pollutants, and you've got to stay below these primary standard levels. Okay, here are the levels. Here are the averaging times that they designate then for these levels, and then there's a secondary standard. For my talk and for the remainder of the time that I have here, I'm going to focus on these primary standards. And specifically, I'm going to talk about the standards associated with particulate matter, 10 microns in diameter and smaller, and PM 2.5. Okay? It's important that you memorize these numbers, okay? As your professor here this morning, it's important that you put these numbers to your heart right now, okay? We're going to talk about these numbers. PM 2.5, 150 micrograms per cubic meter measured an average on a 24-hour basis, okay? 150 micrograms. Now, if you were in my 111 class or my 227 class, I would stop at this point and ask you to recite back that number to me. What did I just tell you the PM10 standard is? Thank you. Particulate matter 2.5 on a 24-hour, the annual arithmetic mean is 15 micrograms per cubic meter. What's that standard for PM 2.5? 15. On a 24-hour basis, that standard is 35 micrograms. What is it on a 24-hour basis? 35. Okay, we've got 150, 15, and 35. Where do these numbers come from? They come from Dr. Arden Pope, frankly. These numbers fundamentally are based on his research. And in fact, I could just be quiet at this point and turn the time over to Arden Pope because he's a legend when it comes to this, okay? He's the one that's convinced the federal government that these are safe levels for you and I, okay? 115, 15, and 35. Effects of particulate matter. This is a picture I took just this last week on March the 30th. I took the picture on the left-hand side at about 4 o'clock in the afternoon. One of the things that we're concerned about, one of the effects of particulate matter is the decreased visibility. And with that also, when we get high particulate matter, as we'll hear in just a little bit here, it also, we see increased incidences of mortality and morbidity rates. The picture on the left, I took this on March the 30th at about 4 o'clock in the afternoon out of my office looking at Y Mountain there. The PM10 concentration was 337 micrograms per cubic meter. You'll remember this last week. Remember when the wind was blowing off the desert here? And you can see there is a mountain back here behind this, I promise. But you can see the visibility is really decreased at this point. What is the PM10 standard? 100 and... Are we in exceedance at this time? When I took this picture, absolutely. Here's the PM 2.5 was 23.5 micrograms as well, okay? So in this case, in fairness here, these emissions here were not caused by anthropogenic sources. This was biogenic. This is the wind blowing. There's nothing that you and I can do about that. But you know, there are other days that we are responsible for things that look like this. Now, fast forward a couple of days. April the 1st is the picture I took on the right-hand side. Same view out my window. And don't count the clouds, but you can see the beautiful mountains there. The PM10 concentration at the time I took this picture was 4.9 micrograms per cubic meter. PM 2.5 was at 5.1. You can see the big difference. I know which air I'd rather be breathing. Let's talk about Utah's issues then. Here's the National Ambient Air Quality Standard. We, according to the EPA, are what are called a non-attainment region when it comes to PM10. I've put a map on here that I've lifted off the EPA's website. You can see all the regions that are highlighted in red and yellow. Red means that they have a serious problem when it comes to PM10. Yellow means that we have a moderate problem when it comes to PM10. But nonetheless, either way, when we exceed the 150 micrograms per cubic meter, we then become what's called a non-attainment area according to the EPA. You can see that Southern California, down in Phoenix area, has a problem when it comes to PM10. But you can see here, it's what has brought us here today, the Wasatch Front has a problem when it comes to PM10, okay? How do we do when it comes to PM 2.5? We talked about PM10. Our bodies have a pretty good way of filtering out this stuff before it gets deep into our lungs. So let's see what happens when we look at PM 2.5. And the story is just as bad. Now, there are some additional regions in the United States. Here, California just has a problem all the way up the coast here. But you can also see that Utah here, across the Wasatch Front, is a non-attainment area, region when it comes to PM 2.5. Here we've got Ohio River Basin and East Coast as well. These guys have a bunch of coal-fired power plants, which causes the problem there. But you can see that Utah has this terrible distinction that we are a non-attainment area when it comes to PM 2.5. Why is that the case? I'm indebted to Dr. Pope for putting together this filter or this figure, and I'll give him the credit for it. What we've plotted here in the upper panel here is the concentration of PM 2.5 in Utah Valley. And you have to give credit to the state of Utah because they've been measuring PM 2.5 and PM 10 for a long, long time. In fact, I think, frankly, they've been at some of the forefronts of some of the states to do this. We're plotting PM 2.5, and the black dots are the 24-hour average concentrations of PM 2.5 since 1998 all the way to about 2007, okay? The red line represents the 30-day moving average through that data, and correspondingly the green line represents the one-year moving average as well. Now, remember I had you memorize a couple of numbers there. And I've drawn a line through here at the 35 microgram standard. This is the 24-hour standard that we're not to exceed when it comes to PM 2.5. And you can see I've drawn another line here through the 15 microgram. That's our yearly average. You can see that if you compare the 15 microgram standard to the green one-year moving average, we stay below that line. That's a good thing, okay? But you can also see that through time, we've begun to creep up a little bit, especially in the last couple of years. We're getting closer to that 15 microgram standard. The reason that we're in trouble when it comes to PM 2.5 is because of these peaks right here. See these black dots that exceed the 35 microgram standard? Now, I'll have you notice, you can see this repeating pattern as we go through the decades here. We exceed these values. This is January 1st of every year. And you can see that it's right about in January that we exceed that 24-hour average. That happens when we get inversions here in our valleys. That's the culprit. When the inversions come, we exceed the 24-hour standard. That's when we get into trouble. Now, the same thing happens in Salt Lake Valley. That's in the lower panel here. Same thing. January into February is when we exceed the 24-hour PM 2.5 standard. That's why we're a non-attainment region when it comes to PM 2.5. Okay, let's look at PM 10. Here, again, in the upper panel is Utah Valley at the Linden Monitor. Now, in the bottom panel here, and this data goes back a little bit later. This is all the way to 1986, 1989. And again, we really should commend the state of Utah because they had the foresight to begin to measure these things. Down in the Salt Lake Valley, we've got what's called the Air Monitoring Center. These guys start to measure these things. This is right off I-15. And then at a certain point in time, they switch over and start measuring at the Hawthorne Elementary School. This is where I'll show you a bunch of data that I've collected up there as well. But you can see for the most part, on the yearly average, we're pretty good when it comes to our 150 micrograms, but our 24-hour average in PM 2.5, we've exceeded as well. Now, there's some interesting things that we can look at in this data. The first thing here, let's look at 1986. We had a whopper over a year. I was not living here in Utah in 1986, but you can see that 1986, there were times there during the winter we got up to about 360 some odd micrograms of PM 2.5. I showed you a picture when you had 300 something micrograms. You wouldn't have been able to see the Utah Lake with this amount of PM 2.5. This is due to Geneva Steel, frankly. Interesting that happened between the year 1986 and 1987. See how we get a big drop in the maximum amount of PM, our 24-hour average is there? And the reason that that happens is that Geneva Steel shuts down for a little while. For about a year they shut down here. And so the amount of particulate matter 10 that we see really drops precipitously here. Now, what happens is that they get financing, I guess, and they come back online again. And you can see back in the year 1988, we start to peak back up here in particulate matter and we stay kind of high. That is until there was a conference held and people were activated and Geneva Steel begins to clean up their act in the years between 1993 and 1994. And you can see the maximum concentrations of PM10 that we see begin to decrease again and the factors start to level off. And this is again in part because Geneva starts to put on scrubbers and other things to reduce the amount of particulate matter that they're releasing. Now, and that happens all the way until the year 2001. Geneva Steel goes out of business for good. And now you can see where we've been at ever since 2001. Now, it's time to talk a little bit about the composition of the particulate matter that's here. And we have a special capability in our group here. It's all fine and dandy to be able to measure the total amount of particulate matter is there, but we can really tease out some very interesting trends and actually begin to understand the sources of this particulate matter if we understand the composition of the particulate matter. And what I'm showing you here is a pie graph, a pie chart, from some data that we collected here in Utah County in 2007 during that big inversion period we had that ran from January into February. And at the time that we made this measurement, we were measuring 65.5 micrograms per meter cubed worth of PM 2.5. Now, what we did in addition to measuring that particulate matter, we use a suite of instruments, and that includes an ambient ion monitor. This is an instrument that allows me to measure the composition of the particles on a 1 hourly average basis. This is a powerful technique. I also at this point are using another instrument called an ethylometer that's allowing me to measure black carbon, elemental carbon. I've got another instrument that's allowing me to measure, again, the total amount of particulate matter that's there. I've also got another instrument called a Dulov and Sunset that allows me to measure the organic content, organic carbon content of this particulate matter, and I can do that on a 1 hourly average basis. And if we put this all together, it allows me to take that 65.5 micrograms of PM 2.5 and distill it down into its molecular elemental components. And this is what we find, is that about 42% of the particulate matter is composed of non-volatile organic material. Okay, this is carbon-containing material. Another 21% of that particulate matter is composed of semi-volatile organic material. If you're not a chemist, it's okay. This is just to distill this down into really understandable terms. This is organic-containing compounds is what this amounts to. Another 29% of that 65 micrograms is composed of ammonium nitrate. And then there's a small component of black carbon. It's the BC. Typically, black carbon is a indicator of diesel emissions from diesel trucks. And then there's 1.7% that's made up of ammonium sulfate. And we can talk a little bit about that. Now, the sodium chloride is on there for a little bit, and it's interesting that we're able to pick this up. During these inversion periods, and shortly before and after, we get big snowstorms. And so the state of Utah comes out and we put salt on the roads. And when the traffic, you guys drive down the road, it kicks up some of this dust, and it then gets incorporated into the particulate matter, and we measure that as well, but the small portion of that. But once we have this elemental analysis, we can then use this with a technique called positive matrix factorization, okay, PMF. This allows us to tease out the sources of this particulate matter. And what PMF looks for is trends in the data is what it looks for. And this is what this all gets distilled down to. We've identified 8 different sources of the pollution here in Utah Valley during one of these inversion events when we're a non-attainment area. The first source is mobile diesel. So these are the diesel trucks that are delivering gravel and other heavy things around the valley. That's one of the first sources of particulate matter here in the valley. We're also able to tease out the difference between mobile diesel and mobile gasoline sources. These mobile gasoline sources in other words, this is the car that you drove here today, is another source of some of the particulate matter that we have here in the valley. Wood smoke is another one. Now, we have gone away for the most part of using wood to heat our homes, but certainly there's a number of you that like to come home and turn on your favorite television show and throw in the wood for ambiance as you watch your favorite show during prime time, and wood smoke is another contributor to that. Road dust is another one. This is driving down the roads. We kick up a certain amount of crustal material. Sulfate associated. You can see that there's these little spikes. This isn't time. I failed to mention that. This isn't time on the x-axis here. We get these little spikes that somebody is emitting SO2 in the valley here. And we don't have any coal-fired power plants here in Utah Valley, and Salt Lake Valley for the most part that doesn't either. And so this is most likely coming from some kind of mobile sources, but it's pretty small. And then we've got these last 3 sources: secondary nitrate, secondary organic material dominated, and secondary organic material dominated. So there's a bunch of sources here that deal with organic material, and I'll talk to you a little bit about where that organic material is coming from in just a second. But it's probably easiest to put this all together into a pie chart here. Here we've got our 65 micrograms again, and now we've used this pie chart to tell us about who are the main contributors to all of that 65 micrograms. And what I'm going to tell you is that about 2/3 or so of the particulate matter that we measure here in Utah Valley comes from either mobile sources, cars, or wood smoke. That's where the secondary organic material is coming from. So what happens is that as your car is driving down the road, it's emitting these hydrocarbons, unburned hydrocarbons. And as you've thrown that wood into your wood burning fireplace or you're burning coal, there's a bunch of organic material that's coming out of the top of your stove. And that material is being converted into these species that I'm just talking about right now. There is a component due to diesel fuel and gasoline. And there is a small component due to road dust and to sulfate as well. Now let's see what the picture looks like up in the Salt Lake Valley. We've gone and done the same kind of study. And in this case, up in the Salt Lake Valley, this is a study we completed back in 2009. Again, we're looking at the composition of the particulate matter during 2 events. During the major inversion event, that's on the left-hand side, and during a non-inversion event here on the right-hand side. Now, during the big inversion event, we get a bunch of particulate matter, PM2.5, 31 micrograms in this case, and during the non-inversion event, it drops to about 1/3 of that. But during the inversion event, you'll see that, again, about 2/3 of the composition of the particulate matter up in the Salt Lake Valley is ammonium nitrate. I'm going to talk to you about a little bit about where this ammonium nitrate is coming from in just a second. There is also a strong component due to what we call missing mass. Now, at the time that we did this study, we had full intentions of measuring the organic molecule component of this particulate matter. Unfortunately, our instrument died out, and so we had to just inference tells us what this is. The missing mass in this case is mostly organic molecule components. And this is most likely, again, coming from mobile source emissions as well as wood smoke. Now, we get the same kind of ratios, although it's a smaller amount, during the non-inversion periods. We get a bunch of ammonium nitrate again, and we get a bunch of organic molecules as well that are coming from mobile sources as well as wood smoke. We can take this elemental content, again, run our positive matrix factorization to try to distill this down into specific sources. And what you find up in the Salt Lake Valley is similar to what we see here. We see, this is on the x-axis, is time of day as well, and this is a relative concentration. And you can see in this case, we get this strong component due to mobile emissions. These spikes in the data represent rush hour traffic. So you get in your car in the morning, everybody's going to get off to work, there's a whole bunch of particulate matter that gets made, you're at work, you're at your office, the particulate matter starts to drop back down again due to mobile source emissions, and then you go home in the evening, you get a big peak again, and then that falls out during the evening, and then we repeat the cycle day in and day out over and over again. Wood smoke has kind of this continuous trend, and usually these peaks occur in the evening when you come home again and people are getting their wood burning fireplaces going. There's a secondary nitrate component as well. Secondary nitrate comes from NOx that's being emitted from people's cars. There's NO, typically it's being emitted. That NO is being converted into NO2, and then through a series of photochemical processes, we produce nitrate. Now, in our valleys here, we have some really interesting chemistry that takes place. We have a bunch of ammonia. That ammonia reacts with the nitrate that we make. In this case, it's in the form of nitric acid, and we make a bunch of ammonium nitrate particles. But again, the secondary nitrate is all coming from cars. We have a secondary nitrate in organic material source. Again, this is due to road traffic again that's making this source. We also have a component due to ozone, and you can see these peaks are occurring right about midday when the sun is at its maximum. We also get a bunch of ozone that's formed, but again, the precursors for making this ozone is, again, mobile emissions, and wood smoke is where it's coming from. And then we also have this last component, age secondary. This is, again, wood smoke and mobile emissions that are going through photochemical processes in the atmosphere and being converted into particulate matter. So what can we do about this? Here's some proposed solutions. Because of, and the first one is meant to be a joke, by the way. And that's why I think they could do it again too, right? They'd be happy to do this. We get into trouble here. If we didn't have these darn mountains, we would be just fine. But these mountains really exacerbate our inversion problems. They act as the sides of a bowl. And so when a high pressure comes in and locks in all this air, then all of this wood smoke and our mobile emissions begin to build up. And when we have this lid on, do this inversion, we can't blow these things out of our valleys. And consequently, the particulate matter and the pollution begins to grow and grow. If we just didn't have the mountains, then the stuff wouldn't get locked in. Our valleys wouldn't act as this big bowl to hold all this stuff in. Now, that's unrealistic to ask Rio Tinto to do this, and they're not going to, and I think we want the mountains. We like to ski and other things. All right, so what else can we do? I think I've given you a lot of evidence to suggest that wood smoke is a primary concern here in our valleys. Even though most of you are not using wood smoke, it's the small percentage, 1 to 3% of you, that are using wood smoke either for ambiance or maybe even to keep your houses warm, that are causing actually quite a bit of the problems that we have here in Utah, in addition to our mobile sources, and we'll talk about that in a second. I'll tell you that the EPA is very well aware of this problem. And so they actually have a program called the Wood Stove Changeout Program. And the EPA will offer upwards of $1,500 for individual users to replace their old wood burning or coal burning stoves to put in an EPA certified stove. When you do that, when you put in an EPA certified model, you decrease the emissions of your stove by over 70%, okay? You get the same amount of heat, they're more efficient, but you decrease the particulate matter by 70%. I looked at the application that's necessary for us to become eligible for this wood stove change-out program through the EPA. And all it asks us to do is it says that if you're a non-attainment area, then you're eligible for this. We are a non-attainment area when it comes to PM10 and PM2.5, and I think it would be very easy for us to become part of this program. If you're not willing to do that, then the other thing that I beg of you to do is to burn only dry seasoned wood. If you have wet wood and you put it into your stove, it does not burn as warm, and it's hot, and it generates a bunch of particulate matter. Now, the other thing, this is kind of a trivial thing, but it works, is to regularly remove ashes from your wood stoves. Okay, if you're not willing to get a new stove, remove the ashes that are in there from before, and there's two reasons for that. One, if you don't remove the ash that's in there, it has an opportunity to get lofted, with convection of your stove back into the atmosphere. But in addition to that, it retards the air getting into your to the fire, and it keeps that fire kind of cool, which makes it more of a sooty fire. So take the ashes out. Those are two things you could do that would reduce the amount of particulate matter that we have in our valleys. Now, Neil Olson at the Department of Air Quality happens to be a buddy of mine. And he sends out every now and again, and maybe you're fortunate enough to get this, you can log onto their website and get these emails, but he sends out what are called air quality action alerts. Now, I've underlined action, Because Neil Olson, when he sends out these action alerts, just begs people, curtail your driving, do not use your wood-burning stoves, especially during these inversion events. Now, at the time that he sends these out, these are suggestions. But I'm telling you, we got to live by, we got to do it. People just, when we get these big inversions, I realize that it starts to get cold. But really, curtailing our driving during these periods, as well as not using your wood-burning stoves, would do a lot to keep our air clean during these big inversion events. Now, when it comes to that, just a note on driving here. Most of the hydrocarbons that get emitted into the atmosphere happen when you're from your car, when you're filling up your gas tank on your car, happen when you're topping off the tank. I know you're guilty of this. I know you are, because you've got a problem out here. You know what I'm talking about, which is you put in the first 15 gallons into your car and you say, you know what, if I can only get in another quarter gallon or a half a gallon, I can go that much further. I'm not going to have to go back to the gas station here. So you get that gas right up to where you can see it there in your gas tank. A lot of that is being volatile hydrocarbons, and it just evaporates into the atmosphere. And you can smell it, right? When you pull into the gas station, you can smell the gas that's there. That's from the hydrocarbons that are being evaporated out of your gas tank. Don't top off your tanks. Really, when the gas pump says stop, stop, and then put the gas cap back on. Public transportation, this is expensive, but I think that Sam probably has to know how to fix this. We need to do more biking, we need to do more walking, and we need more buses, frankly, and we need to convince people to take them, especially during these inversion events. You can do that by carpooling to work. You can also regularly tune up your engines in your cars. This makes a big impact on how efficiently they operate and how many hydrocarbons are coming and NOx is coming out your engine. And something as simply as properly inflating your tires also makes a big impact on how efficiently your car operates. Now, these are just some of the ones that I know that will work, but also we have to give credit to the EPA and to our own Department of Air Quality. There's a couple of URLs that I've put on here. These guys have already thought about this, and they've got some great suggestions about what we can do to curb the particulate matter that we see in our valleys, especially during these inversion periods. And so, like we've talked about, these slides will be posted, and you're welcome, and I would encourage you to go to these websites and implement some of their suggestions that are here. In summary, air quality has improved over the decades, not only here in the United States, but here in our valleys as well, in Utah and along the Wasatch Front. Unfortunately, we still are non-attainment when it comes to PM10 and PM2.5 in Utah and Salt Lake counties. And the way that we can become non-attainment regions is by reducing our mobile and wood smoke emissions, is what it's going to take. I need to give thanks to Professor Delbert Etat, who I inherited a great program from, an emeritus professor here at BYU, and Professor Arden Pope, Neil Olson at the Department of Air Quality. Tyler Cruikshank is a modeler there at the Utah Division of Air Quality, and we've published a number of papers together. I also need to thank the Utah Division of Air Quality. They have given me funds over the years to measure air pollution in both the Salt Lake and Utah valleys, and without their support, none of this would have happened. And I also need to give thanks to Dr. Russell Long and Brett Glover of the US EPA for their contributions in helping us to understand air pollution and helping us with some of these air sampling campaigns. At this time, I would thank you for your attention. I've run out of time, but I'll be here this afternoon and, of course, for the panel. But thank you for your time and your attention. We'll turn the time over to Dr. Pope.
Good job.